But today we're going to finish the week with routing. And we're going to go through static routing and then dynamic routing. Static routing we've talked about. We give the paths, the complete paths, to and from, backwards and forwards. Once you get there, you gotta get back. It's kind of like if you're going from your house to some place that you know where to get to, and you go to Google Maps and you get a map, and I know you're probably going to be using your GPS, but you get a Google map. One of the things that they at least used to have, and I haven't used it for a while either, is a give me the reverse map, because what would happen to me is I'd get there and I'd say, I'll remember how to get out of here. And you know what? I didn't remember how to get out of there. So the reverse map was always something that would be useful. And that's the thing to remember about static routing. And routing really is no different than the routing you would get to go from one place to the other. We have the route tables. We've looked at the content of the route tables. And it just says, hey, where are you going to go to next? And GPS, and I'll jump to the GPS. And that's typically what you have in the GPS. It knows where you're going. It has the map internally, but it only tells you one step at a time what's your next turn. And that's kind of what routers do with the data packets that it's sending. It tells it what's its next turn, what's your next hop, what's your next router, where are you going next when we do those things. So static routing, manually configured routing entry using the IP route, fixed routing paths. A couple of things happen with the fixed routing paths with the static routes. Static routes aren't shared in the dynamic routing protocol. So if you have a route that you don't want shared on your network, you can make it a static route. Keeping in mind that if the topology changes, you got to go back and change the static route. The command to do it, same one that we used for that default route yesterday, IP route, next hop, subnet mask, or IP route, excuse me, not next hop, IP route, the network that we're going to, the subnet mask of the network, and then the next hop address. You also should be able to configure the metrics out here that you want to use to do that, and maybe the next hop and the interface that you want to go out of. Because remember, if you've got an IP address and don't have an interface that it goes out of, the router then has to resolve that. Manually updated if the network changes. Private route unless redistributed by a routing protocol. What redistribution does is allows us to advertise that. And when I say it's not advertised, and that's the default. By default, static routes are not going to be advertised in the routing protocols. If we have a static route that we want to have advertised by one of the dynamic routing protocols, we use a process called redistribution. And the one that we were looking at yesterday was a redistribution, and I redistributed not a static route, but a RIP route into EIGRP. I'm trying to open my packet tracer here, which I'll have to log into, allow me to see what that command looks like. It's nothing really magic, it's just redistribute. And then what we want to redistribute into, and which protocol. Actually, we're going to be in the protocol. Get in a hurry, and then I miss my password. So if it will actually log me in. So what we can do, and the one we were looking at yesterday, redistribute RIP into EIGRP. We could have RIP, we have a router down here maybe that's only capable of running RIP, and it's going to advertise things with RIP. And this one maybe be able to run RIP and EIGRP. We would really want to run EIGRP, or OSPF would be the more preferred protocols on our network. So we've got this guy, and it's going to be connected to other networks. Again, doesn't look like there's anything here, but I've used loopback addresses in order to do that. We've got three or four networks that are running on this this particular router. So when I go into this router, which has got the do the show run, It's a pretty straightforward process. Here, the router, the EIGRP, the router configuration for the EIGRP protocol, and redistribute RIP, and redistribute RIP. And I have some others down here that advertise in RIP to go back to that other device that only was running the RIP protocol. It couldn't get all of this other information. We would then, if we wanted to send all that other stuff here, we'd have router RIP. We could redistribute EIGRP into RIP in order to send all the other stuff to it. But we do have to, and one of the reasons to look at this, we do have to specify a metric, and this would be a redistribute RIP. This would be an EIGRP metric. OSPF has a default metric, which if you don't specify is going to be used, obviously. EIGRP does not have a default metric, so you do have to specify something or it is not going to work. But pretty straightforward command, but a concept to remember: we can redistribute one protocol into another protocol, have one protocol advertise the routes to the other protocol. A translator, if you think about protocols as languages that we speak, think about a translator would be the redistribution. Less bandwidth in dynamic routes, less bandwidth. It shouldn't use any bandwidth because it's not advertising anything. It's not communicating with anything. Once we've configured it, it's there. Unless we, again, do the redistribution from one to the other. It does not use the CPU cycles to calculate updates. The use case when the traffic is predictable and the network design is simple. Predictable, the topology hadn't changed for 10 years, probably not going to change for another 10 years. That's a good use case. When I'm going to the internet, to my ISP, that's a good use case. And that's one where you probably would use a static default route to get there, because you can only go to one place. And again, when you're doing default routes, these shows the IP routes, the same one that we looked at yesterday, which has the remote next hop. But this router A here, it can only go one place. It can only go to router B. So we could tell it, hey, send everything that's coming out of you to router B and let it worry about where to do things. And that's what you and I do at home with our ISP. Everything that we have on our network goes to the ISP, and the ISP then gets it onto the internet for us using more terms here. We're going to have a network route and a host route. A route to a specific network ID, the things that we've been talking about, a network ID, not to a host. And the other one's a host, a route to a specific host. If we have a particularly valuable device that absolutely positively needs a route to it, we can use a host route. And the host route will take us to maybe to a database server, maybe to a file server, whatever we need to do. And the specific route, the subnet mask for an individual address is going to be 32 bits. Look at the whole thing, the network and the host. The network is going to be the entire length of the address. And when we looked at the show IP route, I was going to say IP interface brief. When we did the show IP route, the ones that were the L's, the locals, which is the interface that it's going to go out to get to the C's, the connected networks. They had a 32-bit mask for a host route. The mask is /32 for IPv4 and 128 for IPv6. All ones in the subnet mask. The longest address match possible, and that's the one that we're going to use always. The longest address match possible. So the longest that we could get for an IPv4 is going to be 32 bits. If we put a 32-bit mask in there, it's going to use that route because you can't get a longer mask, a longer prefix than that is. Any packets for the host are processed by the router and then used to specify the path if there are redundant paths, and there may be redundant paths. I've got some, and we'll see what they look like. Redundant paths, multiple paths, which is the best path to take, and that's going to be all based on the metric, obviously. Often created for loopback addresses. Loopback addresses, and to make a loopback address, you just go into the device INTLO. and then whatever you want it to be. INT interface, LO, config, config T into global configuration mode. INT interface, LO1, loopback 1. Interface, LO2, loopback 2. You can make these things. What I've used them for, and then the reason I have a whole bunch of stuff hanging off of some of these simulators, is I've used them to simulate a large network so that I can go in and create routes to do those things, so that we can have a big routing topology that we can use, and you can do the redistribution, you can do the different routing protocols and see what the impact is. The other reason you would use a loopback address would be to do remote management. Loopback addresses never go down, so they're always going to be available. Physical addresses can fail. Somebody could change the IP address. Of course, you could change the IP address on the loopback too, but they could fail. The path to them could get too busy. And you think about this, or I did, say, okay, so what's the big deal? Because if my physical interface goes down, I can't get there anyway. But remember, we're talking about routers. So we may have multiple paths to get there. If we pick the interface to do the remote management with that happens to go down, then we got a problem. If we use the loopback interface, then it's always going to be there. The other thing that loopback interfaces are going to be used for is when we get into OSPF, is for the election. We're going to have another election with OSPF, and it's going to elect this thing called a DR, designated router, and it's going to use the highest IP address on a loopback interface. And we'll go through that process, but it can be used in those elections also. Created for any IP address on the router, we can use these things. This is something that it is in the objectives, and it's like, okay, so I get it, but if we're going to do this, why don't we just use a static in the first place? But a floating static route is a static route that backs up a dynamic route. In other words, we have the dynamic routing protocol, and the dynamic routing protocol calculates a route that we want to go someplace, and we say, hey, if this fails, I need to be able to get there, so maybe in a different direction, so let me make a static route. The thing to keep in mind about this is administrative distance. The administrative distance for the dynamic routing protocols were 90, 110, and 120. 90 for EIGRP, 110 for OSPF, and 120 for RIP. The administrative distance for a static route was 1. And the system will use the route with the lowest administrative distance. So if you configure this floating static, you gotta change the administrative distance to something that's greater than the dynamic routing protocol that you're using. Otherwise, it's going to displace that route. Configure with a higher administrative distance value than the dynamic route, or else it will prefer the static route. Can be used if the dynamic route is lost, and that's what it's for. In the static route, the AD, static routes, those with an AD equal to 1, the administrative distance of 1. Floating static routes, an example here, RIP is a 120. We would need to set the administrative distance to a 121. And the administrative distance is one of the things that is configurable when you do an IP, a static IP route. Static routing, and say, okay, static routing with IPv6, we're going to get into something really cool here, but we're not. We're just going to get into some kind of looks at IPv6. But I would point out we have a colon in here for the address that we go, LO1, loopback 1, 2006, fast Ethernet 00, fast Ethernet 00 for these, and we have the loopbacks down here, LO2, to go to these things. When we want to do routing using IPv6 on these devices, we got to enable IPv6 routing. The default routing protocol, the routing processes that are running on the routers are for IPv4. We enable IPv6 routing with the IPv6 unicast routing command. Nothing really big deal. When we did the switch virtual interface, I had to enable IP routing, and that was for IPv4, IP routing on the layer 3 switch, because when it's born at its heart, the layer 3 switch, the multi-layer switch, the layer that it's using in the multis by default is layer 2. We have to enable all the layer 3 capability on it. The routing tables show IPv6 route, static show IPv6 route, instead of showing IP route. And the thing here is you have to specify IPv6 for everything that's going to be IPv6. IPv6 route, the IPv6 address / prefix, where we had to type the subnet mask 255.255.255.0, whatever it is for the IPv4. We use the / prefix length. We use CIDR notation in the configuration of all of the devices or the IPv6 information. So you don't have to write the subnet mask. We use prefix, and I think all of IPv6 uses the prefix, the / in order to specify the length of the network address instead of the subnet mask. The floating static route, IPv6 route, the address prefix, the interface, and then the administrative distance, because the administrative distance is going to be set greater than whatever the dynamic routing protocol is. The types of static routes, and this is another one that we'll go through, and it is one of the objectives. We have the directly attached static routes, specifies only the output interface. Destined for the next hop, because the destinations assumed to be directly connected to it. And if you think about it, that is something that's going to be the case. If we have our routers here and they're connected together, and we have interface, and this may be gig 00, and this is gig 00, and all this stuff is only going to be significant. All the routing tables, where it goes out of is only going to be significant on the router itself. So if this guy is 192.168.3.2, and we say IP route and go out gig 00, and the interface that shows in the route table is the outbound interface, it's going to go out gig 00. It's going to get to 192.168.3.2. We can do that. So the output interface must be up and have IPv6 routing enabled. The device has to have IPv6 routing enabled. So we can use the outgoing interface to specify that. That's going to be a directly attached static route. A recursive static route, only the next hop address, 192.168.3.2 or whatever the address is, only the next hop address is specified in that one. It's got to be resolved to a valid IPv6 output interface. Recursive goes and finds where it's going to, and then it figures out which interface to go out of to get to that next hop address, and then that interface, that's what the forwarding information base, the switching base, is used for, to switch from interface to interface based upon fully specified static route. We specify both of them. Both of the output interface and the next hop address are specified. Used when the multi-access output interface is used, which makes it necessary to explicitly identify the next hop. The output interface must be up and have IPv6 routing enabled, and the next hop specified must be directly attached. The other thing that I don't think is in this presentation about IPv6 static routes, the next hop address for IPv6 is going to be the link local address. We use the link local address, the FE80 addresses, to communicate with all directly attached devices, the neighbors, the neighbor table. You can see in Windows, and I presume you can in Linux, I've never tried it with it, the IPv6 neighbor tables. Who are your IPv6 neighbors? Which, kind of takes the place of the broadcast protocol, which we don't have. There is no broadcast in IPv6, but static routes for IPv6, the next hop address is going to be static, or the link local address, the FE80 address. There are 20 minutes worth of labs. These are the ones that we did yesterday. The static routes are the addition, the default routes, and those things. What I want to do is to save those 20 minutes worth of labs, and then we'll combine them when we get to the OSPF labs, which is going to be in the dynamic routing protocols. We're going to look at several of them. We're going to look at RIP, OSPF, and EIGRP so that you do know about them. But the static routing protocols, we go in and we configure the routes in both directions to get there and to get back. You've got to do that. And you have to do that for every route. If you think about it, this is where route summarization, or maybe supernetting, where we can combine routes together, would come in handy, or combine networks together would come in handy, where we take the different networks addresses that are on a device, the different network addresses that might be on this guy. So he might have 1, 2, 3, 4, 5, 6 networks that he can get to. So out here, instead of having for the other device, instead of having an entry for each 2, 3, 4, 5, 6, for each of them, 1, 2, 3, 4, whatever there are, an entry for each of the networks, we can, if we're clever, configure this in a hierarchical model, create a hierarchy, I think that's right, a hierarchical model, so that we can group these things together. The thing I was talking about that we did at Roanoke, we had 10.60, and I don't remember what the actual addresses were that we used in network 10.60, and we'll say .0, 10.60.10.0, 10.60.20.0. The network address is 10. And these were in different locations. This might be faculty, student, admin, 10.60.1, 20.0, medical, 10.60.1, 30.0, financial aid, 10.60.1, 40.0, HR. So what could happen at the other end at Virginia Beach is everything that goes to Roanoke, 10.60.x.x/16, 10.60 on the axis, 0.0.0. These are all 24-bit masks. Hierarchy can save you some trouble. The other thing that happens is, here in Roanoke, I add a network, 10.60.160.0. I don't have to do anything up here because it starts with 10.60. Everything with 10.60 goes here. Or actually, everything with 10.60 goes here. And then this guy becomes responsible for the distribution. So IPv4, particularly addressing hierarchy and subnetting, supernetting, moving the subnet mask around, can be important to you when you get into the distribution from one location to the other, multiple locations, or even within your network itself if you're doing using statics and large constantly changing networks, not a good idea. Even in small, constantly changing networks, not a good idea. We really want a stable topology before we go into the static routing protocols. And the ones like the one that I just said, Virginia Beach to Roanoke, yep, we can have a static route. The 10.60 is always going to go to Roanoke. They had other places. 10.50 go to Greensboro. 10.70 might go to Charlotte. They had I don't know, they had 12, 15 different locations that they could send those things to, and when we would go to them, all they had to do was a 16-bit mask, and now, hey, I'm done. I don't have to worry about Roanoke anymore. You go ahead and make as many networks as you want, because everything from here that's destined to you is going to go to you, and then it becomes your responsibility to get it distributed within your own campus. Most networks use dynamic routes but may have one or two static routes configured. For special cases, both can be configured on a router. The only thing that we have to pay attention to, well, there's a couple things we have to pay attention to, but the big one we have to pay attention to is the administrative distance that goes on for these things. The administrative distance is always going to dictate, if we have a conflict, that the static route is going to be used first. We talk about the longest prefix. The longest prefix is going to be used after we decide upon the routing protocol. And we're going to decide upon the routing protocol by using the administrative distance. The administrative distance that is the lowest is going to be the one that's going to be elected. Administrative distance, trustworthiness, reliability, a lot of different terms, but it winds up being the protocol that we're going to use. And the order, EIGRP, or actually the directly connected, we can't change that except the unconnected to shut it down. Then the static, then Cisco's proprietary EIGRP, then OSPF, the standard, the link state protocol, and then RIP, the original protocol that is still available. Dynamic routing, the network protocols adjust the path automatically. Big advantage here, we don't have to worry about it. If something goes down, if we have an issue with something else, or we just move things around, it'll automatically figure it out, and they will share the information with each other, and the network configurations will then be corrected automatically. We don't have to worry about going in and changing the routes on 14 different routers based on either the network traffic or the topology. And the network traffic here, if we start getting congestion, then the systems, depending on the routing protocol, EIGRP uses bandwidth and delay. OSPF uses cost, and RIP uses hop count. So RIP and hop count network traffic is not going to make a whole lot of difference to it. EIGRP network traffic will make a difference to it because its metric is bandwidth and delay. So it will adjust the path if there are alternate paths available for it. If we change the topology, we add a network, remove a network, the interface goes down, interface comes up, the changes are going to take place. The quote advanced unquote EIGRP and OSPF update based on changes. RIP updates based on timing. 30 seconds for RIP v1. Changes in the dynamic routes are shared with the other routers, and then the Cisco routers use the IP routing protocols such as RIP to learn routes dynamically. RIP, EIGRP, OSPF, and again, OSPF is the routing protocol that is the topic of this CCNA exam. So the routing protocols, that we'll look at those when we get back from break. Okay, back to the routing protocols. The types of protocols that we have within the interior, the enterprise, we're going to have distance vector and link state, the first two that are there. The distance vector, RIP v1, RIP v2, IGRP, which is another defunct protocol that keeps showing up in literature. It's an old Cisco proprietary protocol from quite a while ago. I think that it probably went out of use in maybe the late 90s. We had some in the late 90s, early 2000s that had it, but then as we started getting newer routers, it wasn't there anymore. But it advertises the routing table, its entire routing table, to all of its neighbors. High bandwidth, slow convergence, and those are the ones that we kind of have talked about before. If I have my routers here, slow convergence. RIP broadcasts its entire route table every 30 seconds. So what would happen when we would use RIP, if we use RIP, and that's why it's only suitable for small networks, is we have a 192.168.1.0 network. It tells what A, B, C, D, E, A tells B, hey, I know how to get to 192.168.1.0. So B adds it 192.168.1.0 network to its route table. RIP the letter that represents the how it learned it, and then it adds 1 to the hop count, saying it's 1 hop away, 1 router away. The C does the same thing. RIP, it's going to add it, and it'll be, the hop count will be 2. The hop count will be 3. The hop count will be 4. And all these routers are going to then be broadcasting to their neighbors. And 30 seconds, every 30 seconds. So it sends it 30 seconds. 30 seconds later, 60 seconds, we get sent to C. 90 seconds later, we get to D. 120 seconds, 2 minutes later, we finally get down to the end of the line. So when we talk about slow convergence, high bandwidth, slow convergence, we can do that. High bandwidth, lots of broadcast traffic, but remember the interfaces, it'll go out all the interfaces, but the interfaces themselves are broadcast domains. So yeah, high traffic, is it going to go on your network? Yeah, eventually we're going to have our access devices connected to it, and it would be broadcast out all of those. The least preferred distance vector, and the reason it's a distance vector, it's a distance, hops is a distance, and a direction, the vector, the direction that it goes to get that distance, a distance vector protocol. Link state protocols are a little more efficient. OSPF is going to be the one here, and what we're going to see is down here, hybrid is EIGRP, but you don't see EIGRP really in either one of these. EIGRP does have a hop count, but it has characteristics of both. It's going to be called a hybrid protocol, but OSPF is the link state protocol. Big advantage here, advertises only changes to the routing table. So once we get a stable topology, nothing changes. We don't have to update everything. We're not going to be taking the bandwidth. We're not going to be taking the CPU cycles in order to do recalculations. Reduces convergence time. Interface information contains the IP address, the network mask, the network type, the bandwidth, connected routers. Multicast and link state announcements, LSAs, link state announcements, and we can use VLSM. Up here, RIP v1, we talk about VLSM, is classful, which means that it only uses classful networks, the 255, 255, 2550. We can't subnet it, so no subnetting. RIP v2 is classless, which means that we can subnet it. So we have those, distance vector, link state. OSPF is the link state protocol we're interested in, and it is the protocol that we're interested in for. These are interior gateway protocols for both distance vector and link states. Interior means it's for the enterprise, it's for us. We would be enterprise, we would be configuring these. The path vector are exterior gateway protocols, and this is going to be our ISP. It receives information from autonomous system border routers. Table entries contain the designation, network, the next router, the path, and the BGP, border gateway protocol, is the only exterior protocol that we use today. And where do we use this? Oh, the internet uses the border gateway protocol. And the article I put a link into yesterday, border gateway protocol, BGP, route tables were corrupted for the IBM cloud, and it brought a significant portion of it down. BGP, and we have some terms here about autonomous systems and all that. Let me see if I can open a little quickly a BGP here. BGP, yeah, BGP configuration here. Most of the routing that happens get detected from one to the other. BGP is not going to be one of those. We have autonomous system numbers, and these are autonomous system numbers that are assigned to us, and their autonomous system numbers are assigned to us ISPs, big organizations where they have lots of routes to share with each other. So when we do a configuration, and let's just go into this guy and do a show run, we have to specify the autonomous system number, which we'll have to specify in EIGRP, but we also have to specify the IP address of the neighbors. If we do a show IP route, let's see if these things are there, and it's not up and running yet. Let's just show run here and be sure that it actually is configured, and I think it is. Now we just got the adjacency formed with the neighbor 172.14. We specify the neighbor that we're connected to, the IP address of that neighbor, as well as the remote autonomous system. So we have the network 40 here, the neighbors that the router BGP, the network 40. If we go back here, the network 40 is, I think, the one that we're advertising. I think it is. We'll look at one of the others because we have 40 here. 40 is over here, so network 40. But if I show an IP route here, we now have BGP to get to the 40 network via 172.14.0.2, 172.14.0.2. I'm going to go back. I'm going to look at this one real quick and show run. So it be router BGP 79, which is its autonomous system number. It is advertising network 40, and it's the one that should be advertising network 40, not the other one. Typo. The neighbor, it's connected to only one neighbor. The other one, the one in the middle, was connected to two neighbors, so we would specify both of them. But you specify the autonomous system number, which is, again, is assigned centrally, and as well as the IP address that we're connecting to. It's just one of the little kind of quirky configurations that goes on with but the path vector exterior gateway routing protocols routes among different autonomous systems, and it receives the path information from the autonomous system border routers. The table entries contain the destination network, the next router, and the path to get there. BGP, again, is the only exterior gateway routing protocol that we use. A path vector or exterior protocol. Distance vector, we've talked about those a little bit. RIP is the example of the distance vector. The distance, how far the network is, the hop count, and the vector specifies the direction to the network, the exit interface, or the next hop address, or if it's a fully defined, fully specified, both of them are going to be there. Advertise its routing table to all its directly connected neighbors at regular intervals, every 30 seconds for RIP v1. RIP v2 is actually a multicast. So when we're talking about advertising on a regular basis, RIP version 1 is the only one that's going to be doing that. And some people are probably still using it. If you're using RIP now, you're probably going to be using version 2 because it is classless. We can subnet it, and it uses a multicast address instead of a broadcast address to do that. And it had two characteristics. Each router does not have a map of the entire topology. Link state protocols are going to share information with all the routers. They're going to create their own topology table. Each router is going to create a complete topology table of the network. Kind of like, again, going back, if you're using Google Maps and you want to go someplace, you could look at, a small portion or what's the next turn, those sorts of things, but you can get a bigger view to get an idea of what route that you want to take or what route you've been assigned. And the link state protocols are going to do that. They'll have the entire network topology, and then they will calculate the best path, the most efficient path to get from one to the other when we do this thing. But anyhow, distance vector doesn't have that. Each router does not have a map of the entire network, and it uses a lot of bandwidth, slow to converge. When a route becomes unavailable, all the routers, and it sends the entire routing table. A route becomes unavailable, goes back to the things that we talked about yesterday, and I think they're in today's set too. The route poison and the not being able to send it back. to be able to mess things up. RIP, the routing internet protocol, would be the one that does that when we look at it. So that in this one, yeah, I'm back. In this one, these may be a little bit difficult to see, but let's scroll on them a little bit and we can use some, confuse myself later on. But this guy, router A, fast Ethernet 0, 192.168.0 network, is on fast Ethernet 0, and it is 0 hops away. 192.168.10. The 0 here is on 0, and it is 0 hops away. We now put on serial 0 a different one, 0 hops away. But when we start advertising these things, the 192.168.10, each of these is going to be on the interfaces. The hop count will be 0, and this is in the pre-convergence portion of what goes on. Once we are converged, we've shared all of the information. Let's go here to the where is we got the 10, the 0. We didn't send the 0. It's down here someplace else. We got the 40, the 30, the 10, the 0 here on this one, and here we start with the, here's the 0. 192.168, no it's not, it's the 10 network, it's got 0. But when we send it over here directly connected 10, and now we're going to send it over here, we're finally going to get somebody that increases the hop count by 1 on down the line. This guy's doing the 40s from back here, so 1, 1, 2, 3, 3 to get to it here, so the 40 is going to be 3 hops away. They get advertised, and again, RIP v1 every 30 seconds does a complete update of the route table 1 to get from one location to the other when we do those things. So we have pre-conversion for the link state protocols makes routing decisions based on the state of the links. The links are the interfaces, and the states, whether they're up or not, what they're running. The state is a description of an interface and its relation to the neighbors. The link is the router interface when we do these things, and they're going to create a complete map of the network topology, and using that complete map of the network topology, they will calculate the best paths to get through the network. Maybe like you may want to do with Google Maps, you go to look at a bigger one and say, I don't want you to help me, Google. They usually give you 3. Well, I want to look at this whole thing. I want to do my own calculation. Okay, let's put the traffic in and let's put all the delay stuff in so that I can make a decision based on that. And that's what these guys are going to do, is to use all of the information that's available to now build a topology table. From the topology table, they will build their routing table to do these things. They're event triggered after convergence. Initially, there's a lot of traffic going on because they've got to share all this information so that each of the devices can get a complete picture of the network. So all of the devices, all the link state devices are going to be sharing the information with all the other link state devices to create this consolidated picture of the network so that it can make an intelligent decision on what's going to be the path that will be used. They are event triggered after convergence, which is an advantage, so that if nothing happens, we don't do any updates. We don't need to do any updates when we do that. The updates are using multicast addresses via link state announcements, LSAs, and we'll talk about those when we do OSPF specifically, which is the link state protocol. Where they're best, large hierarchical networks, and where convergence time is crucial. If convergence time is crucial, EIGRP is probably the best bet because it keeps track of the backup routes. In link state, if something goes down, it got to go look at the topology table based on the changes and do a recalculation at the time. A router will store a collection of received link state announcements data in the link state database to do these things, and then the contents of the database are then looked at, subjected to, used in the calculation of the Dijkstra algorithm. And that's a term you may want to kind of tuck away someplace. Bellman-Ford was the algorithm that's used in the distance vector. Dijkstra is used in the link state, and then we use the dual in the hybrid in the EIGRP. Accumulated cost along each path is used to determine the total cost of the route, and the routes in the routing table contain a list of the shortest paths to the known destination. OSPF is that protocol. And I think what I want to do is jump the gun again here and let me see if find an OSPF to kind of look at that. OSPF done. So in these things, and I'm going to have the cost table here in a little bit, at least I looked it up the last time. The OSPF uses cost presentation, but it uses cost. And it's going to use each of them just like we talked about in spanning tree. We had a cost, a link cost. We're going to have link costs for these things. So if I am looking here, and let's go to the 10 network, maybe we've got some information going here. I'm going to be sure. Show IP protocols. Yeah, that's what I want to see in adjacency. Show IP protocols will tell me which protocols are running. This is what I didn't see, and that's why I was going to look and see if it was there. But the adjacency OSPF, adjacency's been formed with the neighbor 172.16.10.5. And that is not the IP address. That is the neighbor ID for it. So if we do a show IP route, when we go to the 172.16, we have a administrative distance of 110, and then the cost here is going to be 65. If we go to, this one's interesting, we just go one more, we get a cost of 66. From, let's see, 10 is 66, that's the 172, 192 is 66, 20, both of these are 66. To get to the 16 is going to be 172.16, which is going to be the interface ID, I think, 172.16.10. The serial for the 172.16 to get to it is 66. That's going to be the, and this is 100 meg fast Ethernet, 100 meg connection because we got a fast Ethernet and a gigabit. So we're going to add the cost. Let's see, to get to what up here, 192.168.20. What is its cost going to be? 192.168.20. Those are the 66s, and to get to the 17 to 1610, what I'm looking for is one that I'm not seeing. Probably picked the wrong one to start with. Yeah, let's go with this guy because we've got some serials. Add some passwords here. Show IP route. When we do that, 60. Here's what I was looking for, was the 11 to get to the 30 network. 30 network should be down here, and it is 192.168.30.1. So we have a cost of 11 to get to it, and we have the 66 costs, or the 65 costs. Let's go back here to get to the 72.16.10s. 65, which is going to be the cost for the serial links that we have here, and we have actually it's 10 and then 1 to get across the router that gives us the 11 to get to the other side to do those things. So we have the administrative distance for these things and the cost, and you can add them up. If I go from, let's see if we can add them up. If I go from this guy to the 172.16.10, 172 1610. 110 is a 65, and it should be additive. Am I on the right, the right device? So we'll add the cost of the fast Ethernet to the cost, and actually let's go to 192.168.10 and see if it's any different. 192, yeah, 192, 168.10. That's the one that's the 68. 1610 is the 65 connection to get from one to the other. So they are additive when you look at them going from one to the other. Probably the straight line one that I have. The straight line one that I have is a little bit easier to look at. Yeah, this one we've got serial links and direct Ethernet links going off of this one, and we got gigabit links for it. Take it maybe a couple of seconds here. Okay, we've got them already. Show IP, route, and we have not gotten any adjacencies. Or it says it's got an adjacency, doesn't it? But it still says that everything is directly connected. I think maybe took the other one a couple of seconds, didn't it? If we get these. Okay, now we're getting the adjacencies that I'm looking for. Show IP route. For these things, actually we're not getting these. Process 10. Maybe packet tracer's hating me again. Now they show up. So we have these costs here. We have a cost of 2 that's going to get us to the 10.1.1.3, and that is, I'm guessing, going to be one of these other guys, 10.1.1 here. To do this, 10.1.1.3 is on this interface. So to get to this one, the cost across this gigabit link is going to be 2. If I look at the cost to get to 192.168.1 network. Let's see, oh, that's directly connected, isn't it? Go to the 10.2 network and see if it's this one's in multiple areas, so it gets a little. Okay, 10.2 is the cost of 65. That's what I was looking for here. That would be the serial link cost. If I go to on, but it's not going to work because I've got multiple areas here. If I go, let's say maybe this one to go to one of those 10 networks over there should give us both of those. I'm trying to get one show IP that adds them, that becomes additive to the other one. So the 10.1 is going to be 65. 65 is all across the serial length, and then we're getting into some of these others. We get the 66, and then we got the 2 here, which would be the gigabit. But this would be the serial connection plus the cost to get across the router. Anyhow, a lot of work to a lot of your patience in order to see not a whole lot there. But it does use cost, and that was, I think, what I was kind of trying to show there, the cost from one to the other in order to do theirs. IS to IS is also a link state protocol, but it's not a link state protocol that we're going to be using in this particular certification. The link state trade-offs, the advantages, it builds a topology, a topological map known as the shortest path first tree. So each router will independently determine the best path to get to the destination. Fast convergence, event-triggered updates, hierarchical design, concept of areas, and when we talk about OSPF, we're going to use areas. And what an area is, and this one that I was using had 2 areas in it. You're only going to be responsible for a single area OSPF, but the areas here are everything in Area 1 shares information with all of the routers in Area 1. Everything in Area 2 shares information, or Area 0 shares information with everything in Area 0. We have this thing here is going to be called an area border router, which has an interface in each area, and it can be used to relay the information from one area to the other. But the updating for these guys over here doesn't go to, or in the red area, doesn't go to the routers in the blue area. The updating in the blue area only goes to the blue area, and then the specifics, the relay, so it minimizes the amount of traffic that goes on when we do that, the number of updates that have to go on with these things. Disadvantages is going to take a bigger device in order to run this thing. More memory, more CPU, more bandwidth is required. The flooding of the link state announcements, and this is the bandwidth at startup for the network, can lead to congestion, especially when the routers first start up and they're determining the entire infrastructure that's used for the routing within an autonomous system. An autonomous system, a collection of routers under a common administration. Common administration would be you're the network administrator someplace. You're the network administrator at LeaderQuest, or maybe you're the network administrator at LeaderQuest, Colorado Springs, or Denver, or Dallas. That would be an autonomous system. Network administrator at Roanoke, ECPI, was an autonomous system. Managed the networking within that particular management system, autonomous system. The list of associated networks needs to be advertised before the routing activities can begin. And then the interior protocols that are supported by Cisco are RIP, IGRP, not really anymore. And these are distance vector protocols. Link state OSPF, EIGRP. EIGRP at its heart is a distance vector protocol, but it is going to be called, and you'll hear it called, and we're going to call it, and we're going to say that it is an advanced hybrid protocol. Intermediate system IS to IS, is also a link state protocol. When it says the list of associated networks needs to be advertised before the routing activities can begin, when I go to one of these routers and I look at the configuration, show run, I have a network statement. I pick the one that is not playing in the game. Let's pick a different one. The network statements. When I get down here, I have the networks that I am advertising that are on this device, and there's the 10 network and the 192 network. And then we're going to use wildcard mask, and wildcard masks are basically an inverted subnet mask when I do that. And then the areas that it is going to share its information with, the networks that it's advertising to everybody else. One of the networks that has to be in this list is the network that, or the address of the network that connects to the other devices, because that's what activates the protocol and on the interface and allows it to talk to the other one, the OSPF or the EIGRP or the RIP. So you do have to include the network that the interface that you're going to use, if that makes any sense, that the interface that the interface that's going to talk to the other devices on has to be in that network statement. It has to be on both routers. Exterior gateway protocols are used for routing between autonomous systems. We looked at that a little bit with the packet tracer for the BGP. Service providers, large companies, are going to use exterior gateway protocols. The Internet Exterior Gateway Protocols, BGP, down there is the only one that is in use today, that's in service today. Following information is required, the list of neighbors. When we looked at the configuration, we had to specify the neighbor, autonomous system number, a list of neighbors or peer routers, which we're going to change information with. We had to have the IP address, the networks that we're going to advertise, the local router's autonomous system number, as well as the remote autonomous system number. And that's the list of the neighbor or peer routers that we're going to need to exchange information with. BGP, the only currently viable, only currently used exterior gateway protocol today. A BGP topology, it's going to be a big topology because that's what we're going to use them for. We have these things that are connected, and you notice that they're connected to maybe 2 or 3 but adjacent autonomous systems. Each of them has a different autonomous system number. And we normally don't share information with these with remote autonomous systems, although you can. Special configuration. Hybrid routing protocols use distance vector metrics but emphasize the more accurate metrics than the conventional distance vector. Generally, we're going to say that it has characteristics of both distance vector and link state protocols, and EIGRP is the hybrid routing protocol that we use. Converge more rapidly than the distance vector protocols. Don't incur the overheads of the link state updates. It's going to be event triggered rather than triggered by periodic updates. Still, periodic updates back to RIP shares the entire route table with everybody on a regular basis when we have those things. Exclusively a product of EIGRP, the Cisco proprietary protocol that we use. RIP, distance vector class full routing protocol, uses hop count as a metric for path selection. 4 basic components: routing update process, triggered RIP routing metrics, routing stability, and routing timers that are going to be used for it. Its advantages: it's easy to use, router RIP, and then the network statements. You don't even have to put a subnet mask in for these things, or a wildcard mask. Compatibility with diverse network devices, legacy devices. Windows servers has used or been able to use or been able to do routing, talk to RIP routers for years. I think in the newer versions of the servers, they also support OSPF, so you're not obligated to use that. But if you have older devices that don't support, or weaker devices, because one of the things that we needed, the disadvantage was we needed a more powerful device in order to use the OSPFs and the EIGRPs of the world. Disadvantages: RIP v1 is classful. The hop count greater than 15 is infinity, so it's only can be used on small networks that aren't going to go very far. Split horizon, route poisoning, and hold down mechanisms are going to prevent routing loops on these things. And we talked about these a little bit, split horizon, what I couldn't remember a little earlier. Split horizon, you can't tell somebody something that they told you. You can't send a route back to a router that you got from it, which would then prevent you from going back and forth, the little one that we looked at yesterday, to allow these things. So in RIP here, an autonomous system would be like you or I are managing a network, and we put RIP on. Our autonomous system would be all of our networks that we're using or sharing RIP speaking devices. If I wanted to go to a different autonomous system, then I would need a BGP, an exterior gateway port protocol, in order to do that. And the BGP shows there the border gateway protocol, exterior gateway routing protocols connect together autonomous systems. The differences between RIP v1 and RIP v2 here, the message format that we use for these things. And this is one, again, this is good to know information. I don't think it's anything you're going to be tested on in the certification, but the RIP v1, the command, the version, the family, the network address, and the distance fields. RIP v1 uses class full addressing. RIP v1 broadcasts messages every 30 seconds. RIP v2 uses all of the RIP v1 fields, and it has 3 new fields. It has a route tag, the subnet mask, and the next hop address. v2 is classless addressing. We can subnet it, because up here one of the things that's added is the subnet mask, which allows us to do subnetting with it. And it uses multicasting instead of broadcast in order to send the messages. And I think when we looked at those multicast list of addresses, RIP v2 was one of those. Passive interface is a command that's used to disable the interfaces if you don't have any RIP devices, or maybe you're running a protocol in your infrastructure and you don't want that. Maybe advertise things to your ISP. You can make the interface that goes to the ISP passive, which means that it's not going to be sending out. It may accept, but the router will accept, but it's not going to be sending out notifications or communicating with a router with the same protocol. RIP v2 and RIP next generation. RIP next generation, 1993 authentication, key management, route summarization, classless internet domain routing, and VLSM. It's also going to support IPv6, the RIP v2. RIP v2 is not, RIP next generation is. Supports automatic route summarization by default. Route summarization is if we have multiple devices, maybe subnetted networks, they're automatically summarized at the classful boundary as they cross the classful boundary when we send them out. Makes it a little more efficient. Can cause a mess also. Unlike RIP v1, we can disable it in RIP v2 with a no auto summary if we don't want that to happen. The commands, version 1 enables version 1 only, version 2 enables version 2 only. If we have no version, we don't do a version statement, we're going to send v1 updates, but listen to both the v1 and the v2. And the default is going to default to version 1, so version 1 will take v2 updates, v2 will not take v1 updates. RIP next generation, and the IPv6 component of this, although I think that, and I have heard they say, oh, they weren't going to put a RIP in IPv6, but they did. RIP next generation, same thing based on RIP v2, 15 hops, hop count, 16 becomes infinity. Administrative distance is still 120. Supports IPv6 addresses. And it uses a multicast address FF02::9. It's going to be a multicast protocol. No advertising, IPv6 networks. We have to still do the IPv6 unicast routing in order to turn it on. Just like you're always going to have to do in these devices in order to turn on IPv6 routing, IPv6 unicast routing. The interface IPv6 RIP, and then the domain name. When we look at OSPF, I want to show you the differences between IPv4 and IPv6 other than the addressing. The way we configure it is different. We go to, instead of using the network statement that we just saw, we go to the interface to configure it. RIP has a number of timers. The routing update timer controls the sending of the messages. It's going to be every 30 seconds. Counts down to 0 and then sends the updates again. Reset to 30 seconds. Route invalid timer problems when no update is received within 180 seconds of the last update. The failed route is set to 16, which is going to be for these things. The route hold down timer, after we have the bad route, is the time in seconds during which the routing information about better routes is suppressed. I'm not going to take any route updates. The hold down timer is going to be there, and it's going to be 180 seconds. The route flush timer, the time interval before the route is purged from the route table, we're going to be 320 seconds. So when we look at the entire thing, the invalid time, the hold down time, the purge time, it can be a long time before a route actually gets taken out of the route table in the RIP. IGRP, I want to click through this one pretty quickly. Legacy Cisco proprietary distance vector software. It's not here anymore. EIGRP is based on it. Developed in 1984, replaced by EIGRP in 1992. So in the year 2020, we're probably not going to find any of these anymore. Maybe you will if you have something really old. It supported multiple protocols. IP, obviously, we still have. IPX, we don't have. DECnet. AppleTalk, I'm not sure if AppleTalk is still available on the Apple devices, but they're using IP like everybody else. It supported other protocols that are no longer in use. A hop count for it was 100. It advertised every 90 seconds, which meant that we didn't have as much traffic, but we had a much slower convergence time. Composite of 5 different metrics, and they're going to be K values. Those are still used in EIGRP. Less bandwidth than RIP, converged slower than RIP because of the 90 seconds. Recognize different autonomous systems. This was the zeros and the autonomous, no, wrong. Autonomous system numbers, which we assigned. My brain got crossed there. Autonomous system number that we assign. These are different autonomous system numbers than we would use for the big networks, the big devices, where the individuals, the large organizations, the ISPs, would be assigned the different autonomous system numbers. We assign the autonomous system numbers. We have a group of routers that we want to share routes with, and we still use this concept in EIGRP. This thing automatically summarized at class full boundaries, and we could load traffic, could load balanced traffic across unequal, equal, or unequal metric costs. The default is going to be for equal cost load balancing. We can configure it as unequal cost load balancing. So the next thing that we're going to do is OSPF.